So, dear class 11 students, we are starting new chapter, Binomial Theorem today. So, what is binomial? An algebraic expression that contains two terms is known as binomial. Like here I am writing some binomials. So many binomials will be there. So, etc. So these all are the expressions these all are the algebraic expressions that contain two terms. So these are called binomials. Now this x plus a is taken as standard form of binomial. X plus a is taken as standard form of binomial. So now we observe, okay, we raised this x plus a to some integral powers, and let us see what happens. And this is x plus a whole power 0 is 1, x plus a whole power 1 is x plus a, the x plus a whole square, if you see, x square plus 2ax plus a square. If we observe x plus a whole cube, x cube plus 3ax square, are you following? 3a square x plus a cube. If we go for x plus a whole power 4, x power 4, 4x cube a, 6x square a square, 4x a cube plus a power 4. Like this you get. These all are the expansions of the binomials raised to the certain integral power. Now if you observe the coefficients, these coefficients follow, okay, when the index is 0, the coefficient is 1. When index is 1, the coefficients are 1 and 1. When index is 2, the coefficients are 1, 2, 1. Are you following? When index is 3, the coefficients are 1, 3, 3, 1. When index is 4, the coefficients are 1, 4, 6, 4, 1. Okay? So 1, 4, 6, okay, 4, 1. Like this, if you observe all these expansions, the coefficients are following certain pattern. Okay? So now I'm cleaning this board. So the coefficients are following certain pattern. So suppose now index is 5, okay. So let us write here that pattern clearly here. So index of the binomial, okay. Index of the binomial, the coefficients in the expansion. See, the coefficients will follow that a certain pattern. That certain pattern has been given as a table, and if you observe that coefficients, it is expanding like a triangle, and this pattern was discovered by Pascal. So B. Pascal. So it is in the form of a triangle. See, the triangular shape. So it is called as Pascal's triangle. So here it is easy to expand for any integral power. Just keep 1 and 1 in the extremes, and you keep on adding like this. So see here, 1 plus 1 gives you 2. It's a triangle now. Now, are you following? 1 plus 2 is 3. It's a triangle again. 2 plus 1, 3. So like this, okay? 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. So like this you have to go. 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. So you have to keep 1 and 1 in extremes, and you have to add like this so that you can get the coefficients. So till here I followed the same procedure. So 1 plus 5, 6. 5 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1, 6. So in a binomial expansion, the coefficients can be obtained, okay, from the Pascal's triangle. But we know we don't use this, in fact, because suppose the power is 15, say you cannot go up to 15, it is time consuming. Right, up to 15 you cannot write this table. Suppose the power is 25, you cannot go until 25, it is time consuming. So this has become an historical note, but the practical usage is not that much with this, because up to 6 the coefficients the students can itself remember. If they use once or twice or thrice, that coefficient values will be in students' mind. Other than that, for higher powers it is time consuming, and without writing from the beginning you cannot go ahead. Okay, so there is no so much use with this okay, you have to understand, but you have to know what Pascal is trying to say. Okay, what was his discovery? Okay, from this discovery what you can learn, okay, what you can get. So those and so factors you should know, understand. Now dear students, now we are discussing binomial theorem for positive integral index. This was discovered by Newton. So the theorem says, if n is any positive integer, then x plus a whole power n is equal to nc0 x power n, this is nc1 x power n minus 1 into a plus nc2 x power n minus 2 into a square plus so on plus NCR x power n minus r into a power r plus so on plus NCN a power n. So this is called binomial theorem for positive integer index. So if you carefully observe, the Newton gave the NCR notation for coefficients, and that NCR how to find you have learned in combinations. So the same formula you have to use here to get that NCR value. And then if you observe, the x power is starting with the index of the binomial and gradually it is decreasing by 1, and at the end it is disappearing. So x power becoming 0. Now if you observe a power, the way it has started with 0 here, there is no a, so a power 0. So gradually it is increasing by 1, and finally, okay, it has ended up with a power n, which is the index of the binomial. So x power is starting from n going to 0, a power starting from 0 going to n. One is decreasing order and the other is increasing order. And now in each term you can see the sum of the powers of x and a. If you see the sum of the powers of x and a in each term, it is n minus 1 plus 1. This is n plus 0, n minus 2 plus 2, n minus r plus r, n plus 0. So in each term, okay, if you take the sum of the powers of x and a, it is getting n. So here that NCR x power n minus r a power r is known as general term of the binomial expansion. General term of the above binomial expansion is tr plus 1 is equal NCR x power n minus r into a to the power of r plus 1th term. And the number of terms in the above expansion is n plus 1. Number of terms in the above binomial expansion is n plus 1. As this suffix is here, the suffix is started with 0, ended with n. So for each suffix you are getting a term. So n plus 1 terms are there. Did you understand? Now as note number 3, if you take this binomial theorem x plus a whole to the power of n in terms of summation notation, it can be written as summation NCR x power n minus r a power r, summation ranging over r ranging over 0 to n. So the binomial theorem, this is in the expanded form. The same expanded form, okay, can be expressed in using summation notations like summation NCR x power n minus r a power r, summation ranging over r ranging over 0 to n. Understood? The students, next already we learned this expansion. Now if you go for minus, what will happen? It is also same, but you see the alternate sign changes, that's all. So are you following? So when is any positive integer, then we have x plus a whole power n is this, then x minus a whole power n will be this. Suppose if you go for, so I'm going to add this now. If you go for addition, what happens, you see. So now this, if you go for addition, this one, this with suffix 1, with suffix 3, all the terms gets cancelled. So with suffix 0, 2, all the terms will be doubled. So if you take 2 common, then you will have nc0 x power n plus nc2 x power n minus 2 a square plus so on. You get like this. Suppose if you go for subtraction now, if you go for subtraction, the symbols get changed. Then the suffix 0, suffix 2, suffix even number terms are cancelled. Suffix odd number terms will be doubled. So 2 into nc1 x power n minus 1a plus nc3 x power n minus 3a cube plus so on. You get like this. So x plus a whole power n plus x minus a whole power n is this. X plus a whole power n minus x minus a whole power n is equal to this. Understood? So now about number of terms. About number of terms now. So this is 1, this is 2. These are the expansions. So when n is odd, both 1 and 2 will have same number of terms. Which is equal to n plus 1 by 2 terms will be there. If n is odd, both 1 and 2 will have same number of terms, which is equal to n plus 1 by 2 terms. Okay? Now, when n is even, are you following? When n is even, so when n is even, the first expansion will have n by 2 plus 1 terms, number of terms I am talking. And the second expansion will have n by 2 terms. So this is the most important point that you have to remember. So if n is odd, both 1 and 2 have same number of terms, n plus 1 by 2 terms will be there. When is even, the first expansion will have n by 2 plus 1 terms. Second expansion will have n by 2 terms. Now, if you are interested to get the number of terms in the expansion of ax plus by plus cz is whole to the power of n. So the number of terms in the expansion of ax plus by plus cz whole power n can be derived as, so the derivation is not so important, just you remember that derived as n plus 1 into n plus 2 by 2. Okay? So the number of terms in this expansion can be derived as n plus 1. For example, find the number of terms in 2x minus 3y plus 5z whole to the power of 20, say. So this formula you have to use. Number of terms is equal, number of terms in that expansion is equal n plus 1 into n plus 2 by 2. 21 into 22 by 2. So 21 into 11. So 21 into 11. 11 1 is 11. 11 2 is 22. 23. So you get 231 terms. So if you expand that 2x minus 3y plus 5z whole power 20, you get 231 terms. Understood?